Okay, we're going to continue on here. Last time we talked really about stoichiometry and kind of finished up stoichiometry, percent yield, um, limiting reagents problems. So remember that as we talked about, there really is, when we're doing stoichiometry, kind of four basic steps for a basic stoichiometry problem, which is balance your equation, convert to moles, do your mole to mole relationship from the equation, which is really the stoichiometry there. And lastly, take those moles to some other unit. Remember that if it's a basic stoichiometry problem, pretty much you're just given one piece of information about somebody in the equation. And that could be a product, could be a reactant, and so forth. You can just really follow these steps to get there. We also talked about limiting reagents, and excess reagents. And again, limiting reagents and excess reagents are important because in a reaction, there will always be some reactant that gets used up first, and that is your limiting reagent. And one that we have plenty of, you'll have some left over, is your excess reagent. And the way that you again can identify it is a limiting reagent problem, because again, they will not always, in like blinking lights, tell you you are doing a limiting reagent problem. The way you really know is when you look at the information given to you. If you can, from that information that's given to you, pretty much get those units or information into moles, and you have moles of the starting reactants, then you know it is a limiting reagent problem. And as we talked about, you do need to do a calculation to determine the limiting reagent. We talked about a few different ways to sort of approach those problems. One way is really our same basic four steps, but right around here, you determine the limiting reagent. And really in this sort of a process, if you do this, you will basically figure out how much of one reactant is needed to use up all of the other reactant. And you'll do just a basic stoichiometry calculation between the two reactants. And once you figure out how much is needed to use up that first reactant, you then can compare it to how many moles you have of each reactant to start with. And if you have enough, then that's your excess reagent. If you do not have enough, then that is your limiting reagent. The limiting reagent is important because it is the one that determines how much product you can produce. So you always want to, when you're doing a calculation based on how much product you're going to yield, you always want to do it based off the limiting reagent. So that's why you do have to sort of calculate. Once you do that, you would then take your limiting reagent and kind of continue on with our four steps. The other very popular way nowadays is, again, just to do two separate stoichiometry calculations, one with the first reactant to the product and one with the second reactant to the product, and see whichever one produces the least number of grams of product will be both your theoretical yield and your limiting reagent. Or the third way that we talked about is the ice table way. And again, with the ice table way, um, we could use that ice table and basically just do a very simple calculation at the end to figure out which one's your limiting reagent, whichever one produces the smallest x value in your table. And the benefit, again, as we talked about with the ice table, as we saw maybe with some of those examples, was you can super quickly really answer every question you might be asked, which is, how much product you produce, how much of the other product you produce, how much of the excess reagents left over. So it's a very useful sort of thing. Remember that when you do a calculation from the equation based on how much you start with, that is a certain type of yield, and that is what is known as the theoretical yield. So the theoretical yield is your maximum yield. The actual yield is what you actually get when you do the experiment. And if you divide those two and times it by 100, that gets you your percent yield, which again is typically we're looking for a large number for percent yield, not a small number. Any questions on any of that stoichiometry stuff there? All right, so continuing on with this mix match of information, we're going to kind of go to, and this was the one I think we finished up on. We're going to then talk about kind of concentration, solutions, and we're going to talk about solution stoichiometry. So first off, a solution is a homogeneous mixture, and it's a mixture of two or more substances together. And really, when we talk about a solution, those are the ones that get the aqueous symbol next to it. So when you see something that has like the AQ symbol or aqueous symbol next to it, those are solutions. They're homogeneous, which means they mix together. You don't see different phases or layers or anything like that. And there's really two parts to a solution. There is the solute, which is the smaller part of the solution. That is typically the thing that's dissolved. And the larger part of the solution is the solvent. So for example, again, if you took water, which is a pure liquid, not aqueous, because it is a pure substance by itself, it is not a mixture. And if you take something like, again, like sodium chloride, that salt will dissolve in the water because it's polar and ionic coming together. And that will form together a sodium chloride solution that would get the aqueous symbol next to it. So again, a mixture of those two things. In this case, the solute would be the sodium chloride, and water here would be our solvent in this case. Water is a very common solvent. It's a good solvent for a lot of things, like ionic things, polar things, as we'll talk about maybe in a later chapter as well. It's not a great solvent for things that are non-polar. So although we use water a lot, it's not always the right choice when you want to make a solution. When we talk about solutions, something like a soft drink, major component is really water. Then obviously we have other things kind of dissolved in your soft drink. Air, major component of air is actually nitrogen, followed by oxygen, argon, methane, and whatever else you got kind of in the air you're breathing. And soft solder, there is a lead with a little bit of tin in it as well. So sometimes we oftentimes think of solutions as being sort of liquid, but you can sort of relate a solution to something like a gas or something like that as well. So with solution stoichiometry, we oftentimes will use probably the most common unit of concentration, which is molarity. And molarity is big M there, moles per liter. You should think of molarity really as like a formula, if you will, because a lot of times we are given or we have two of the three pieces of information. So a lot of times we just sort of rearrange it to solve for other things. If you want liters, that is going to be the moles divided by the molarity. If you want moles, that's going to be liters times molarity. That is, again, something that is used a lot in chemistry, is that conversion right there. It absolutely does need to be in liters, the volume, when you use it with molarity. And that's because if we look at sort of the units here, liters times molarity, which is moles over liters. So when you times those two things, the liters cancel and we end up with moles. I would highly recommend as well that if you have a molarity, you should use it like a conversion factor. You should also take more of a dimensional analysis approach when using it, and not use it with the big M. And the reason for that is, let's just say, for example, you had 4.5 molar sodium chloride solution. You would want to use this probably like so 4.5 moles per liter of sodium chloride. And again, the number stays with the moles and it's always per 1 liter. You could also flip it around if you're going to do some dimensional analysis. So why do I recommend you kind of get rid of the big M and use both of these units? It is because for the most part, lots of people always forget about the volume. They have no idea about the volume. They're not sure where it is. They're not sure if they should multiply, divide. Frankly, they just see the big M and start thinking moles, and that's all they think about, and they have nothing to idea about the volume. So you should probably get rid of the big M when you're doing a calculation, do a more dimensional analysis sort of setup. That way you will for sure see your units that are there. And again, when you're using it, because this is really moles per liter, the volume should always be in liters when you're using molarity by itself. Now, can you multiply molarity times milliliters? The answer is yes. but you do not get maybe the number you think you're going to get. So if you take milliliters times molarity, you do not get moles. You get its friend, the millimole. Yeah. And that's about 1,000-fold off probably what you think you want to use that number for, and your number is going to be really off in this case. So you cannot, you should probably not multiply by milliliters unless you sort of know what you're doing. But in reality, molarity can also be millimoles over milliliters. So it's all good if you use milliliters on the bottom, the milli on top, and the milli on the bottom cancel, and you're back to moles per liter. So just keep that in mind. If you're using molarity by itself, definitely I would go make sure it's in liters, because probably 99.9 times or even more, you're going to need moles to continue on, not millimoles. And again, you're going to probably be off if you don't understand that or kind of miss that conversion. Any questions on that there? Other common kind of conversions that we use with molarity, obviously, in a lot of cases, you're given grams. So if you want to calculate the molarity, you need to convert grams to moles, and that's again our molar mass from the periodic table to do so. And I would say very commonly as well, um, like the equipment that we use in the lab, for example, most of the time volumes are given to you in milliliters. So a lot of converting from milliliters to liters is oftentimes a very common conversion that you use a lot with this. Once again, 1,000 milliliters equals 1 liter. So again, that is super common sort of conversions that you sometimes I need to do. Any questions on that there? So let's calculate the molarity of a solution that's prepared by dissolving 15.6 grams of KBr in enough water to make 1.25 liters of solution. Potassium on the periodic table 3910, and our friend bromine 7990. So why don't you take a moment and see what you come up with here. Which is moles per liter. And in this particular case, we actually have the liters part given to us. We actually don't even need to convert it to liters. It's already in there. So we definitely have that part. We do need the moles part. We do not have that, but we do have 15.6 grams of KBr. The KBr, by the way, is our solute in this case, and our water is our solvent in this case. And in this case, we would need the molar mass there to convert our grams to moles. So basically, we're just going to add these two together. I think that's going to give me a buck 19 grams per mole there, basically. So we'll take our 15.6 grams of KBr. Again, just kind of taking a dimensional analysis approach here. I'll put grams on the bottom so that they cancel. Moles of KBr up on top. Again, multiplying and dividing. The grams will cancel. That's going to get us here 15.6 divided by 119. Looks like 0.131 moles. That is going to be the top part here that we need. So we got everything we need to calculate our molarity now. So again, our molarity would be 0.131 moles divided by our 1.25 liters. And we will end up with here, it looks like 0.105. Now, again, in terms of the units, you could leave it as moles over 1 liter. Again, the number stays with the moles part. Or at this point, you can revert back to the big M if you like, and a little KBR action maybe as well as we do that. Any questions on that calculation there? All right, let's take a look at another one maybe here. What is the mass of Ki that's required to make 500 milliliters of a 2.8 molar potassium iodide solution? So again, potassium 3910 and iodine a little bit more, 126.9 here. All right, so see what you come up with here. Okay, let's take a look. So again, in this case, we got a couple of pieces of information given to us. We obviously have a volume we want to make of 500 milliliters. We have a molarity of 2.8 molar. And we're looking for really how many grams of Ki is required. So clearly molarity is involved, which is our moles per liter. I have volume, I have molarity. So again, it would make sense to rearrange this and solve for moles. Once I have moles, I could definitely get to grams using the molar mass to do so. The moles here again would be our liters times our molarity. Once again, a couple things we need to kind of work on here. First off, the molarity here, I would convert into a kind of usable conversion factor. We could say we have 2.80 moles per liter. Or again, if you needed to flip it around, you could use it like a conversion factor like so. Again, you can see both of the units. Also, as we were talking about, in order for everything to properly cancel out, we do need to convert our volume into liters. So we'll take our 500 milliliters divided by 1,000, move the decimal place 3 places to the left there. Going to give us 0.5 liters. Again, taking a dimensional analysis approach here means, frankly, you don't have to worry about rearranging this equation. It'll just kind of do it for you. So if I take the 0.5 liters, all you have to remember again is opposites cancel. So liters are up on top. To make it work, we would need liters in the opposite location, which is on the bottom there, and moles per liter of Ki. Again, we multiply the top, divide the bottom. Liters cancel, and that will give us how many moles of Ki we need, which in this case looks like it's 1.4 moles of Ki. Again, now that we have it in moles, we could use the molar mass there from the periodic table to get us to grams. In this case, we're just going to add these guys together. So it looks like 3910 plus 126.9, about 166 grams per mole. Using that as well as a conversion factor, we will go opposites cancel. So we're going to go 166 grams per mole on the bottom. Again, multiplying and dividing. Moles will cancel. And that means here, take that times 1.4. I'll call it about 232 grams of Ki is needed to make this solution. Yeah. Questions on that there. So if you were going to make the solution, you would weigh out about 232 grams of the Ki. You would take some water, dissolve it, maybe use something like a volumetric flask like you did on day 1 of titrations, and put it into your volumetric flask, fill it up to the 500 milliliter mark, and you will now have a solution that has a molarity of 2.80. Yeah. Any questions on molarity or how to calculate molarity here? Now, another aspect of molarity is sometimes we may not be interested in the whole compound, if you will. We may be interested in the concentration of ions that are floating around in the solution. By the way, that is where you find ions, just basically floating around in the solution part. So, for example, let's just say we had our sodium chloride solution, and let's just say it did have a molarity of 4.5 molar. In solution, because it's a strong electrolyte, it is not going to stay together. It's going to completely break apart into sodium ions and chloride ions, basically. So again, 100%, you're just going to have ions floating around in that solution. And in some cases, we may be interested in the concentration of those ions that are actually floating around in the solution. So the relationship of the molarity of the whole thing to the molarity of the ions kind of works like really stoichiometry and kind of a mole-to-mole relationship. So for example, it is a 1-to-1 relationship between the whole thing and the sodium ions that are going to be floating around. How that works with molarity is you basically take 1 times 4.5, and the concentration of the sodium ions in that solution would be 4.5 molar as well. If we were interested in the chloride ions, it's a 1-to-1 relationship between those two. And that means you would take 1 times 4.5 molar, and that's going to give us 4.5 molar as the concentration of chloride ions that are floating around there. Obviously here, molarity here is not additive, so 4.5 and 4.5 does not equal 4.5, but sort of proportional. It's like a 1-to-1 relationship. You get one of each basically in there. So the concentration of those ions are the same. If I had a calcium bromide solution, when that breaks apart, we would get a calcium ion and 2 bromide ions in solution. So once again, in solution, you're going to have calcium ions and bromide ions basically floating around in that solution. So if I again maybe had a 4 molar solution here of calcium bromide, probably put a 2 there would be great as well. This is a 1-to-1 relationship between the whole thing and just the calcium ions, which means the concentration of the calcium ions in this case would actually be 4 molar for our calcium ions. But when we look at the bromide, it is a 1-to-2 relationship. So the way the concentration gets adjusted is 2 times the molarity, and that would give us 8 molar of our bromide ions in this case. So this is the quick way to do it. If it broke apart into a 1-to-3, you would times the concentration by 3 or so forth, basically. Now, the reason we do all this sort of multiplying by 2 or 1, again, this is sort of the short way of doing it, just multiply by the coefficient. The actual calculation, if you did it sort of outright, would look like this. We would take 4 moles per liter of calcium bromide. And we actually would do a mole-to-mole relationship. It's a 1 mole to 1 mole relationship. 1 mole of calcium ions for every 1 mole of your calcium bromide. The moles of calcium bromide cancel, and that leaves us big equals 4 moles per liter of our calcium ions. So again, that is how we get to sort of that 4 molar. If we did our 4 moles per liter of calcium bromide, it is again a 1 mole to 2 mole relationship. So using that relationship there, 2 moles of Br minus from every 1 mole of calcium bromide. The moles of calcium bromide cancel, and we end up with our 8 moles per liter of our bromide in this case, as well our bromide in this particular case. So the quick way is really just multiply by the coefficient. It really is a kind of mole-to-mole relationship is really what you're doing when you do that. And like I said, sometimes you may come across questions that are not interested in the whole thing, but just an ion floating around or something like that. Any questions on that there? So again, multiply by 1, multiply by 2, basically. That's where those numbers basically come from. All right, so why don't you, for these 2 solutions here, what is the concentration of all the ions involved? 2 separate solutions. So for the first one, what is the sodium concentration and what is the sulfate concentration? And for the second one, what's the potassium concentration and what is the chromate concentration? So take a moment and calculate that. And we will get a couple of sodium ions floating around. And we will get 1 sulfate ion floating around. So if we do know that this concentration of the whole thing is 1.2 molar, it is a 1-to-2 relationship between sodium ions and the whole thing. And that means we would take 2 times that 1.2 molar, and that would give us that it is 2.4 molar in terms of its sodium ion concentration. And when we look at sulfate, it is a 1-to-1 relationship, which means it is 1 times our molarity, or 1.2 molar. Any questions on that one there? Looking at our potassium chromate here, same idea. We'll figure out how it breaks apart here. So K2CrO4. And again, it's going to give us 2 potassiums and a chromate here as I squeeze it in there. In this case, 0.75 molars, the whole thing. It is, again, a 1-to-2 relationship between the potassium ion and the whole thing. So we would take 2 times our 0.75 molar, giving us 1.5 molar for our potassium ions. And for our chromate, it is a 1-to-1 relationship. Let's come down here. So we basically take 1 times our 0.75 molar, and that will get us here our 0.75 molar there of our chromate ions. Any question on how to relate molarity of the whole thing to individual ions? All right, so let's take a look here then at, again, you made a solution like this the other day, but typically if you want to make a solution, a volumetric flask is a good thing to use, usually 2 decimal places on that, right? And again, put a little bit of solid, some water. Want to keep it in the bottom of the flask like you did, kind of mix it really good, get it to start to dissolve. Once it does dissolve, you want to take it into the neck of the flask. Again, not going over that line, right? Because as we talked about, it's already dissolved, so you can't just dump stuff out. Otherwise, you will not have the right molarity. So give it some mixing and not too much shaking, and you should have hopefully the proper solution. Another process that's used with solutions is dilution. And a lot of times solutions come in really concentrated forms. They're sometimes referred to as stock solutions, pretty high concentration. By the way, we see a high concentration number or a big number next to the M, like 18 molar. That's pretty strong, right? Then we get a large number, and molarity, right, is at the top part there, which is stuff reacting, would be a big number, right? So if you have 18 molar hydrochloric acid, there is a lot of hydrochloric acid dissolved in there, right? Because its concentration is high. The smaller the number is with the M, the less of that solute you have in there. So we do a process known as dilution, and in a process of dilution, we basically add more solvent to it. So we add more solvent to your solution. And what that means is the moles of the solute before you do dilution should be the same as the moles of solute after you do the dilution. You're just adding more solvent. And what that does, again, if you think about molarity, which is moles of solute over liters of solution, when you add more solution or really solvent, remember a solution is made up of 2 things, the solute and the solvent. So when you're adding more solvent, you're actually increasing the bottom value here in the molarity. And when you do that, we start to see the molarity decrease because now we have a larger number on the bottom divided by a smaller number up on top. Our molarity starts to come down. So in a dilution, really the only thing that you add is, again, more solvent. A lot of times that is water, but not always. But that is typically what you add. There is a dilution equation, which is M1V1 equals M2V2. This is usually before the dilution, and this is usually after the dilution. Really doesn't matter as long as you keep the numbers together. Now, this equation is commonly used because the most common unit of concentration is molarity. So M1V1 equals M2V2 is typically what we use. You will also sometimes see this equation written as C1V1 equals C2V2, where C is just a generic concentration. And although molarity is the most common unit of concentration and probably the value you use the most with this equation, You technically could do it with other concentration units. So, for example, if you had percent mass to mass of the solution, you could do it with that, percent volume to volume. Other concentration type units can actually be put into here. So, sometimes you'll see people use C1V1 equals C2V2, more of just a generic concentration on each side. Now, in this case, this equation, if you are using the dilution equation, it should be a dilution happening is typically when you should use that. You should not just use that in all situations where you have two molarities and two volumes. Especially later on when we talk about some solution stoichiometry, you might get lucky, but not all the time will you get lucky. So you should not use it if it's not a dilution. The other thing is, as we were talking about earlier, if you are doing some type of calculation with molarity by itself, so molarity by itself, you definitely want to convert that volume to liters. But if you are using this formula, you can leave, if you like, your volumes in milliliters, and it'll just be milliliters on both sides. So it works out okay. Why does that work out okay? Let's just say we're solving for M1. We get M2 divided, our times V2 divided by V1. We have molarity times milliliters divided by milliliters. Milliliters cancel, we're back to molarity. So it works out okay. Same thing if you did volume and solve for volume, it'll work out okay. The difference is if you leave your volume here in milliliters and put it in there and you're solving for volume, you'll just get milliliters. If you use liters, you'll get liters out if you do that. Any questions on that there? All right, so how would you prepare 60 milliliters of a 0.2 molar nitric acid solution from a stock? All right, so we are doing a dilution here, and if you're not sure, well, we want to make a nitric acid solution from a nitric acid solution, so there is no reaction or anything happening. This guy is more concentrated, right, than what we want to make. So basically what we got going on there is we got a nitric acid bottle sitting, and it has a molarity of 4 molar. And usually the ones in that sort of dilution equation, M1V1 equals M2V2, are the more concentrated. But once again, it doesn't really matter as long as you keep the numbers that go together. We definitely want to make a new solution that has a volume of 60 milliliters and a molarity of 0.2 molar. And these guys will be my twos since they are the lower concentrated or more dilute solution. So if we just kind of check off, we got these guys, we got this, we clearly are missing V1 in this case. So we could do that. V1 would equal M2 V2. We're going to divide this to the other side, and that's going to give us M1. Again, as I mentioned earlier, we can leave our volume here in milliliters if you like, or you can convert it to liters. But this is going to give me 0.2 molar times my 60 milliliters divided by my M1 here, which is 4 molar. The molarities are going to cancel, and like I said before, we will end up with milliliters in this case. And we got 0.2 times 60 divided by 4. It's going to give us about 3 milliliters here. First off, any questions on that calculation so far? That 3 milliliters is our 3 milliliters of our nitric acid. That is the 3 milliliters we're going to take from the more concentrated solution and dump it into our new solution that we're going to make. So we're going to pop in there about 3 milliliters of our nitric acid that is more concentrated. Now, should I, in this particular case, should I add 60 milliliters of deionized water to this to complete it off? I should not, because if I add 60 milliliters of water to this, I now have my total volume of 63 and not 60. Yeah. So a very common question is in these dilution type problems is how much water should you add? So typically, if you want to know how much water or solvent, you typically will take your V2 minus your V1. So the V2 is what I want to make, which is 60 milliliters. V1 is what I already tossed in there, which is 3 milliliters. That would tell me that in order to make this solution properly, I should probably toss in there about 57 milliliters of water with it. So if I do that and I toss in there 57 milliliters of water, 57 milliliters, 3 milliliters gives me my total volume of 60. Give it a nice little mix, and now we should have a solution that has a concentration of 0.2 molar. Any questions on that there? So you definitely want to make sure when you're going through sort of dilution problems that you do read them carefully, because sometimes they may ask for how much of the more concentrated solution you need. Sometimes they may ask how much water you need to add to it. And sometimes they may just ask what the new molarity is as well. Any questions on that there? All right, so let's try this one here. What volume of water is needed to make 500 milliliters of a 0.25 molar calcium nitrate solution from a 5 molar solution? Okay, so let's take a look. Once again here, we're going to make a calcium nitrate solution from a more concentrated calcium nitrate solution. So again, that's a dilution M1V1 equals M2V2. Very similar to the previous one, we have a solution of calcium nitrate that has a concentration of 5 molar. And since that's a little more concentrated, I'm going to call that my M1. We want to make, again, a separate solution that has a volume of 500 milliliters and call that V2, and a molarity, which is M2 that goes with it, 0.25 molar. Once again, here we are missing V1, so that is what we're going to solve for. So again, V1 in this case, M2 V2 divided by M1. That's going to get us here 0.25 molar. Again, I'm going to leave my volume in milliliters. All that means is my answer will be in milliliters in this case. And we'll take 5 molar. So we're going to cancel here and obviously do that little calculation there. I feel like it's 25. Let's see here. 25 it is. So that does equal 25 milliliters of our calcium nitrate solution. Once again, typically when you solve for V1, that is how much of the more concentrated solution you again are going to dump into here to your new sort of bottle. And here we do want to know how much water again. So the volume of water in this case will be V2 minus V1. So that is 500 milliliters minus 25 milliliters. That means we do need to toss in there about 475 milliliters of water with it. So 25 milliliters plus 475 milliliters of water. That's going to give us our 500 milliliters. And again, if we mix it up pretty good, we would have a concentration of 0.25 molar in this case. Any questions on dilutions? Yeah. So again, common errors people make is they don't realize it's a dilution and don't use the formula. Second common error people make is they use that formula everywhere where they have 2 molarities and like a volume. So don't use it. Only use it in this situation for a dilution. Questions on dilutions? All right, so now that we talked a little bit about molarity and dilutions, and we talked about stoichiometry, we're going to talk about calculations involving solutions and stoichiometry. And one sort of process that we actually don't do here in the school in this class is one thing is, for example, we could do a precipitation reaction, and that's what's known as gravimetric analysis. And when you add two solutions together, it's going to form this precipitate here. And if you want to isolate the precipitate, you could throw that into the old Buchner funnel, hook it up to a vacuum, which is why there are vacuums in labs. And you hook it up there and it will suck through all the water, liquid part, and your solid, which is the white solid in this case, would be trapped up there in the funnel. On a piece of filter paper, you could dry it out and figure out how much you actually produced. Um, and again, that would give you your actual yield, right? If you actually physically did this. You could also obviously do a stoichiometry calculation and figure out basically what your theoretical yield should be based on what you're starting with. So when we involve sort of stoichiometry that involves solutions, be it two solutions, one solution, maybe we make a solution. Uh, in terms of stoichiometry, we do pretty much our same four steps. We still balance our equation. We still convert to moles. We still do our mole to mole relationship from the equation. And we still take those moles to some other unit. Now, typically speaking, if you have some solutions involved, I would say in a lot of cases, not 100% of the time, but in a lot of problems, right around here, instead of doing our normal grams to mole conversion, using the molar mass like we have done previously, a lot of times we may use molarity and volume and solve for moles, which would be liters times molarity. So again, if you have some solutions involved, we sort of get to the moles a different way by using volume and molarity rather than grams and molar mass to get the moles. I would say also a lot of times at the very end of the calculation, we have gone from moles to grams, once again using the molar mass. Also at the end, we can deviate here and go from moles to say volume using our molarity equation because you may know the molarity and you may now know the moles, so you can figure out the volume. We may also use the moles to actually calculate the molarity. So maybe you know the volume there, and you can use the moles and the volume to get to the molarity. So kind of at the beginning, sometimes we'll use the volume and molarity to get the moles, and at the end, instead of just kind of figuring out grams or something like that, we may figure out something like volume or molarity if it's more of a solution sort of ending. You should always also think about whenever you're doing any type of stoichiometry problem, be it the ones we've done previously, ones involving volume, ones involving gas, whatever it may involve, you always want to also think about limiting reagent. Is the limiting reagent a problem or not? And you definitely can have one in a solution situation that is a limiting reagent. You can even have one in gas situation that's limiting reagent. You could even have units when you do stoichiometry that are mixed, like we got grams for one reactant and like volume and molarity for the other. So you could have kind of all kinds of mixtures of things that can happen. So you always want to think about it. If it is a limiting reagent problem, you could solve it like we've been talking about, however way you want to do that, ice table it, just do the stoichiometry calculations, limiting reagent type calculations, what we talked about. So let's take a look at one here and which I feel like you have one on your sheet, and I feel like I don't know where mine went. But is it after this, maybe? No, it is not. I don't have that one in this. Let me steal that one that I was just gonna do there. I'm gonna find it here. I think I got it here on the handout here. Yeah, yeah. So let's take a look at the one that I think is in the handout, which is if you mix 25 milliliters of 0.25 molar potassium chloride with 15 milliliters of 0.525 molar lead to nitrate. Aqueous and aqueous. How many grams of lead to chloride would you produce? Would you produce there? All right, so why don't you take a moment here and give it a go. And again, even though there's solutions and stuff, like I said, you want to kind of still follow your same stoichiometry type of calculations and see what you end up with. I'll give you some numbers that maybe will help, and then we'll go through it here. Lead is 207.2, and chlorine is 3545. I think that's all you probably need here. All right, so give it a go, see what you come up with here. I'll give it a go too myself. Hopefully it'll come up the same answer. Seen so clearly it's a stoichiometry problem, and clearly the first step, no matter what sort of process you're going to do, is you need an equation. So we'll start with that. So I have some potassium chloride. I'm going to react it with lead to nitrate. This should be recognizable to you because that's an ionic compound, that's an ionic compound. So this should be a double displacement precipitation reaction that's going to happen. So we are going to switch partners, right? That always happens. This is the only type of equation or reaction that occurs. Remember that we do not want to write the formulas and balance at the same time. We want to get the right formulas down. So again, the basic unit of this guy is those two ions. The basic unit of this one here is these two ions. So when we put them together, we should end up with KNO3, which would be aqueous because it's nitrate involved and potassium. And when these two come together, we again should end up with this guy, which will be insoluble, as lead to is one of the exceptions for chloride, bromide, and iodide as being insoluble. First off, any question on that there? Now that we have that, now we should go back and balance, and it does look like perhaps I need a 2 there, and maybe a 2 there as well. Any questions on that there? All right, so step number 1 is complete. We have our equation. I think I'm just gonna erase this so I got a little bit more room to work with here. Get rid of that too, maybe. Next thing is after we have the equation, we want to take whatever they gave us and convert to moles. So we know we have 25 milliliters of our KCl, and it has a molarity of 2.5 molar. We also know that I have 15 milliliters here of my lead 2 nitrate. It has a molarity of 0.52 molar. Well, I could definitely get moles here, right? And I could definitely get moles here because if I think about molarity, I have the molarity and the volume, which means I could calculate moles. That means I could get moles of both reactants, which means what type of stoichiometry problem is this? This is a limiting reagent problem. So again, they're not going to highlight that with pretty pictures or anything like that. But here, because of the information given to us, we could get to moles. This is a limiting reagent problem. Yeah. So somewhere along the way, we are going to have to calculate which one is the limiting reagent. Before we get there, we still need to do number 2, which is convert everybody into moles. So we're going to convert these guys into moles with our second step. We do have to convert our volume here into liters. You could divide it by 1,000, right? And if you take your 25 milliliters divided by 1,000, milliliters is a liter, you'll get 0.025 liters. Remember that when we take our molarity, we're going to get rid of the big M and use it as moles per liter. And I'm going to do a little stoichiometry and not really stoichiometry, dimensional analysis here. 0.25 moles per liter of my KCl. And that is going to get me, looks like 0.025 times 0.25. 0.00625 moles of KCl. So I'll do the same thing here for my other reactant. So for my lead 2 nitrate, also going to divide my volume here by 1,000 or move your decimal place 3 places to the left. Gets me 0.015 liters. Going to times it by its molarity, which also I'm going to take out of the big M and use as moles per liter. And that would get us here 0.525 moles per liter of my lead 2 nitrate. Liters are going to cancel, and we will end up with here 0.0150 times 0.525, 0.00788 moles of our lead 2 nitrate. So this again is very similar to what we do in a normal stoichiometry problem. Instead of taking grams of molar mass to get moles, volume and molarity gets us our moles. Any questions on that so far? All right, now it's up to you how you want to do it. You can figure out the limiting reagent however you like to do it. I'm just going to roll with the ice table like we've done previously. So I think I'll go, can I go that way? Man, I can't go that way. Yeah. Maybe I'll just erase this page here, borrow that. There we go. Borrow that there, I think. All right, so I'm just going to rewrite it here. So we got 2 KCl plus our PbNO3. Going to make our KNO3 and our PbCl2 solid, and we had some balancing going on there, 2 there, I think, as well. All right, so to figure out our limiting reagent here, we're going to do the little ice table. So KCl, we have 0.00625 moles. So 0.00625 moles. For our lead 2 nitrate, we had our 0.00788 moles, and again 0 and 0. Change is what takes into account the stoichiometry, so minus 2x because of the coefficient. This is going to be minus x because the coefficient is 1. This will be plus 2x because the coefficient is 2. Coefficient here is 1. This would be plus x. That means as we come down here to the end, 0.00625 minus 2x, 0.00788 minus x, 2x, and x. Once again, any questions on the table there? Remember, we still just have to do a really simple sort of calculation here to figure out our limiting reagent. So we're going to set each of these guys equal to 0. And we're going to solve for x. So we'll do that. That will give us basically 2x equals 0.00625 divided by 2. Going to give us basically an x value here of, looks like 0.00313 moles. This is just going to be x is equal to 0.00788 moles. Remember, it is the smallest number of moles that we're looking for. And in this case, that is the x value, so we don't need that. That tells us this is our limiting reagent. This is our excess reagent in this case. Any questions on how to solve that there? Now that we have that, we can really focus in on our product, which is this guy here. And we could clearly see at the end in our table, the lead 2 chloride will equal X. So the moles of PbCl2 will equal X. And since X equals that number, that means we have 0.00313 moles of PbCl2. We do want grams, so we will need the molar mass of PbCl2, and that lead is 207.2. 207.2 grams per mole plus 2 times 3545 for our chlorines. Going to give us a molar mass here for our product. By the way, that would be our theoretical yield in moles of our product in this case, plus 207.2. Looks like about 278.1 grams per mole. We will use that as our conversion factor. I'll just go maybe right about there, I think. 0.00313 moles of PbCl2. And again, 278.1 grams per mole from the periodic table. Going to tell us here in grams, our theoretical yield will be, looks like 0.869 grams of PbCl2. Again, our theoretical yield. Any questions on that? Again, if you don't do the ICE table, you could do 2 separate calculations to the PbCl2 and see which one yields you the smallest amount of grams, which should hopefully match that number. You could also do the other approach that we talked about and to figure out the limit reagent. Any questions on that? So hopefully you can see it really is the same 4 steps. Balance the equation, convert to moles, figure out our limiting reagent, and then basically do our mole-to-mole relationship.